Okay, let's just dive right into this. When you picture a massive star dying, you're probably imagining a giant spherical explosion, right? Just a standard supernova. But what happens if you take that dying star, spin its core to absolute dizzying speeds, and then thread it with unbelievably intense magnetic fields? Well, you don't just get an explosion. You build a literal cosmic hyper-engine. Welcome to this explainer on magnetorotational supernovae. Today we're going to decode the exact mechanics of the universe's most powerful stellar engine. We are stepping way beyond ordinary astrophysics here, right into a realm where magnetic fields completely dictate the fate of the cosmos.
Here's the blueprint for how we're going to tear down the mechanics of this hyper-engine today. Number 1. Beyond ordinary stellar explosions. 2. Ingredients for magnetic core collapse. 3. The magnetorotational instability engine. 4. Launching bipolar jets and hypernovae. 5. Forging heavy elements and GRBs. And finally, number 6. Spotting a magnetorotational supernova. Let's get right into it.
Section 1. Beyond ordinary stellar explosions.
So to really appreciate the sheer power of a magnetorotational supernova, we kind of need to establish how a normal stellar death works first. Look at the stark contrast here and how these two models actually trigger an explosion. Over in a standard core collapse supernova, the explosion relies on this delayed neutrino heating mechanism. Basically, the collapsing core forms a proto-neutron star, and a shockwave bounces outward. But that shockwave stalls out. It literally has to wait to be re-energized by a slow, simmering boil of neutrinos radiating from the core. It takes time, and the resulting explosion is relatively spherical. But then you look at the magnetorotational mechanism. It bypasses that wait time completely, no stalling. It directly taps into the rotational kinetic energy of that newborn compact remnant. It's a prompt, violently fast process driven entirely by magnetic stress.
Section 2. Ingredients for magnetic core collapse.
So you might be wondering, if this magnetic mechanism is really that powerful, why doesn't every dying star just explode this way? Well, a massive star doesn't just stumble into these extreme conditions. It requires an incredibly specific, rare set of ingredients to build this kind of magnetic bomb. And the absolute most crucial ingredient is spin. You see, rapid rotation is usually lost over a star's lifetime because stellar winds couple with the outer envelope and just bleed away that momentum. By the time most single stars finally collapse, their cores are spinning way too slowly, maybe with a period of tens of seconds. But for our engine to work, we need a core spinning with a millisecond period, literally milliseconds. This perfectly illustrates how binary star systems come to the rescue. Through tidal spin-up in close binary systems, a core's rotation can actually synchronize to the orbit. Or we might see binary mergers, like two helium cores merging together. Astronomers have actually observed systems like HD 45166. It's a helium star with a massive 43 kilogauss magnetic field, which is perfectly setting the stage for magnetar formation. Even the accretion-induced collapse of white dwarfs can conserve enough magnetic flux to jumpstart this whole engine.
Section 3. The magnetorotational instability engine.
All right, so once we actually have this rapidly spinning, highly magnetized iron core, gravity finally wins out and the core collapses. Let's zoom into the microphysics here and break down exactly how this detonation happens, step by step. During the collapse, the conservation of angular momentum causes that newborn proto-neutron star to spin furiously. But here's the kicker. It doesn't spin uniformly. The inner layers spin much faster than the outer layers, which is a process we call differential rotation. Stage 1. Because the magnetic field lines are basically frozen into the plasma, this differential rotation physically drags and stretches the magnetic field azimuthally. Imagine winding a rubber band around a really fast-spinning spool. The field starts growing linearly. Stage 2. That rubber band gets pulled so incredibly tight that it just snaps into a chaotic, unstable state. This is the magnetorotational instability, or MRI, which triggers exponential growth of the magnetic field. And then Stage 3. The magnetic pressure becomes so immense that it acts like a giant piston, driving a massive magneto-hydrodynamic shockwave outward.
I want to focus on that middle step for just a second. The magnetorotational instability triggers a violent snap into exponential overdrive. The magnetic field strength literally skyrockets until it reaches equipartition with the rotational kinetic energy. We're talking up to 10 to the 15th Gauss. To put that into perspective for you, that is a quadrillion times stronger than Earth's magnetic field. A quadrillion. Now, the sources do note that pure MRI can sometimes be disrupted by secondary parasitic shear modes, which is basically just complex fluid dynamics trying to ruin that coherent growth. But when that happens, convective and turbulent dynamos deep within the star just take over the heavy lifting to ensure those mind-bending magnetar-level fields are still reached.
Section 4. Launching bipolar jets and hypernovae.
Okay, so we've got an incomprehensibly strong magnetic field inside this spinning core. What actually happens when all that immense magnetic pressure finally overcomes the dense gas pressure of the dying star? Well, we see a massive geometric shift. Notice how the velocity field in the simulation isn't just a simple sphere. The magnetic stresses actually launch highly collimated, incredibly fast-moving bipolar jets straight out of the poles of the star. It completely transforms a spherical collapse into a directed, axial explosion. And the extreme temperature map right next to it confirms this exact thing. You can see this fiery, elongated channel just punching right through the stellar mantle.
And this is absolutely crucial. The efficiency of this engine is staggering. Roughly 10% of the rotational kinetic energy of that proto-neutron star is converted directly into the radiokinetic energy of the explosion. Now, 10% might not sound like a lot in everyday terms, but in this context, that is massive. It's enough energy to eject entire solar masses of material and easily account for the intense energies we see in the universe's most powerful stellar explosions, known as hypernovae. Section 5. Forging heavy elements and GRBs.
Let's zoom out from the microscopic fluid dynamics for a minute. How does this cosmic engine physically alter the universe around it? Have you ever actually wondered where heavy elements, like the gold in your ring or platinum, come from? Well, the extreme conditions inside these magnetic jets serve as a literal cosmic forge. Because these jets are moving so incredibly fast and contain matter with a very low electron fraction, which just means it's highly neutron-rich, they trigger what physicists call the R process, or rapid neutron capture process. Neutrons bombard seed nuclei so rapidly that they literally don't even have time to decay, synthesizing incredibly heavy elements up to mass 195 right there inside the jet itself.
And the engine leaves behind some pretty spectacular byproducts too. If the core manages to stabilize, it leaves behind a magnetar, a highly magnetized neutron star. Those jets punching through the star, they can also generate long-duration gamma-ray bursts, which are the absolute brightest electromagnetic events in the entire universe. We get all those heavy R process elements I just mentioned, and fascinatingly, if the newborn neutron star is simply too massive to hold itself up, it undergoes a two-stage collapse, losing angular momentum and eventually falling completely into a black hole.
Now, this all sounds totally incredible in a supercomputer simulation, right? But it does raise a very practical question. How do we actually observe an invisible magnetic engine that's buried deep inside a collapsing star millions of light years away? I mean, we can't exactly just stick a telescope inside it.
Section 6. Spotting a magnetorotational supernova.
This is where the real detective work of modern astronomy comes in. We have to look for specific, multi-messenger fingerprints. For instance, when we analyze actual neutrino luminosity data, notice that sharp initial spike, followed by a gap, and then a broader second peak. This distinct double pulse was famously observed in supernova 1987A, with a 4.5-hour gap between the signals. Models suggest this perfectly matches the exact two-stage collapse we were just talking about. First, the core collapses into a rapidly rotating neutron star, and then, as it bleeds angular momentum to power the magnetic explosion, it undergoes a secondary collapse straight into a black hole. But neutrinos are just one piece of this giant puzzle. Because those intense magnetic fields deform the proto-neutron star into an oblate, sort of squashed shape, the neutrinos emitted are actually pushed to much higher energies, which alters the diffuse supernova neutrino background. We also expect to find circularly polarized gravitational waves. When the core's rotational energy exceeds a certain critical limit relative to gravity, it triggers a low T/W instability. Essentially, the core starts wobbling violently with non-axiosymmetric spiral motions, and that churns out distinct gravitational waves. And finally, we look at prompt polarized light. This is by far our best way to measure the physical shape of the explosion at the exact moment it breaks out of the star.
Which brings us to a massive, really recent breakthrough, Supernova 2024 GG. Astronomers actually managed to capture unprecedentedly early spectropolarimetry data just 1.2 days after the shock breakout. Because they caught it so early, the polarization of the light directly revealed that the explosion had a persisting prominent symmetry axis. It wasn't just a messy, chaotic spherical blob, it was a highly organized axial explosion acting on a massive scale, which is exactly what the jet-driven magnetorotational models have been predicting.
The researchers who analyzed 2024 GG actually started their report with this beautiful quote. Since the beginning of physics, symmetry considerations have provided us with an extremely powerful and useful tool in our effort to understand nature. And it's so true. Measuring the very geometry of a supernova's shock breakout gives away the fundamental physics driving the core explosion. It literally tells us that this magnetic hyper-engine was turning.
So what should you really take away from all this? Why does any of this matter to us? Because the abstract astrophysics happening inside these magnetic cores isn't so abstract after all. The heavy elements here on Earth, the gold in your jewelry, the platinum running through our electronics, and the most unbelievably energetic gamma-ray bursts lighting up the distant cosmos are the direct physical result of these rare extreme magnetic engines. They are, quite literally, the ultimate cosmic forges.
We've seen exactly how rotational energy and magnetic fields can completely hijack a dying star, but it does leave us with a pretty incredible lingering thought. Could the very engines that forge our heaviest elements also hold the final key to unraveling the universe's most extreme magnetic mysteries? As our multi-messenger observatories continue to grow more sensitive, we might just be on the verge of catching these hyper-engines right in the act. Thanks so much for joining me on this explainer, and as always, keep looking up.